I will talk about early detection of service abuse, some kind of service abuse with Redis. I'm Michał. I work at SoftwareMill. I do stuff with computers and with people there as well. So the problem that we are gonna look at, or more like a challenge, because they taught me that it's not a problem, it's always a challenge. So it frames things a bit differently. So the challenge that we are gonna look at today is the problem that we may potentially have in one of our projects for one of our customers. It's not on a production yet. It's not a production-ready solution. It's just in the phase of a research. We are trying to figure out what patterns, what solutions, and what approach would be good for that. So they are trying to figure out how it would look like when implemented. So the thing is that we have some kind of service. The use case itself is pretty simple, but it kind of generalized to a lot of different similar cases. So the use case is pretty simple. We have our service on the right in the cloud, let's say, and we have a bunch of users. And let's say that we are a SaaS company. We are selling service licenses, service software as a service. So you subscribe to our service, and for that you can use some kind of a voucher code, some kind of coupon, or some kind of, I don't know, pre-generated URL, so that we know who are you from. So let's say, for the sake of simplicity, that is just a voucher code, some promo code that you got from somewhere to get some discounts on our services. So the use case is pretty simple, because what we need to do basically is first, just to, whenever the request comes in with a voucher code, just to register or subscribe to our service. First, we need to validate the voucher, and then we need to use the voucher, like start the service, and then mark the voucher as used, because we don't want the same voucher, because they are unique. We don't want the same vouchers to be used multiple times. And as you can see from the picture, there are at least two places that can hit the database, because we have the database somewhere in our chain. We need some storage. So there are at least two places where we need to hit our operational main database. The first one on the top, we need to validate the code the code against the available codes in our pool. Then do our core business logic, let's say, so activate the service, charge users, do all that stuff, and then mark the code somewhere in the flow, mark the code as well as used, so that no other users can use the same code. The next part of the challenge is that there may be attempts to from maybe fraudulent, or maybe some kind of users that are unaware of that fact, to try to abuse the service in a way that they can try to reuse the same code over and over, just to get some more bonuses, just to get some different accounts on our service with a discount, whenever they are not supposed to do the stuff. And in this case, we obviously validate the stuff at the beginning, and we should reject the request. That's pretty easy. But the thing's getting hairy. The moment when we are getting popular, we are getting tons of users. Our service is really popular. We are getting tons of load, and within this amount of load, there is more and more fraudulent requests, attempts to fraud, attempts to reuse the same code, attempts to trick our systems into the way to give the users the bonuses they should not get. So what are the challenges that we may face in here, like in this scenario? Within our infrastructure, I'll go back to the first one. There's a reason that these arrows are kind of fat and red here, because it means there's a lot of these fraudulent requests and a lot of kind of hit on a database that we should try to avoid, ideally, because we know if we know they are fraudulent requests, we could somehow avoid them. So what challenge do we have? Performance penalty on frequent DB requests. If you have tons of users, if you have tons of malicious requests amongst the requests that are coming to your system, you may hit the penalty of database lookups, and that may slow down entire system or entire subsystem, depending on how you have your deployment structures. So performance penalty is the first one. Then database, at some scenarios, database may be a serious bottleneck. impacting all the different use cases and all the different activities of users in the system. Increasing cost of database interactions, especially when you're in cloud, because in cloud it usually pay for either incoming, outgoing traffic, or number of requests, number of queries, and all that stuff on a DB. So you naturally want to reduce the cost, you want to save the money, and you naturally want to lower the amount of database interactions. So it's minimum that's only necessary. And unnecessary internal traffic. Again, sometimes you may, in a cloud environment, you may also pay for the internal traffic in the network. So these are all the challenges that we may face when your service is growing, when you have big business and really popular services. So basically what we want to do, we want to go from the picture on the left to the picture on the right. So like filter out some stuff on the somehow at the beginning, just to have only the correct requests, only the valid requests at the end. But currently we have the scenario where all three phases hit our main database. That's why the database suffers. That's why our rest of our services suffers. And that's not a really good, that's not a real use case. And we want to go from here to there, wherever we have, to the scenario where we have something at the beginning that kind of shields our service, like filters out all that stuff that is malicious, and leaves the database free for the other services, for our core business, for our core functionalities, like registering users, serving users, doing the stuff that is core of our business. So how can we get there, and why the heck I'll steer the at least 2 red dots in there? Why we cannot filter all the fraudulent requests at the beginning? The thing is that if we do at scale, if you work in a really like simple scenario, a really small service, you can afford to serialize all the requests, like handle them one by one, and then you can guarantee all the consistency of the data. Then you can be sure that you only validate the data and know eventually consistent data is in there. But if you are on a big scale, you cannot really serialize the operation. You need to parallelize them somehow, and because of that, you need to embrace some form of eventual consistency there. So whenever you check something at the beginning on the very first stage, it doesn't really mean that between the time that you checked them and said it's okay, the code wasn't already used in the other stages of the process. So this is a form of eventual consistency here in play, and we need to embrace them when we want to scale that stuff. So there are also other distributed systems problems if we want to go the bigger scale, all the microservices, all the network traffic, all the faults, and all that stuff that's related basically to physics. Like if you send one stuff from one computer to the other, it can be only as fast. Different sources of truth, they are not always in sync. So as I said, the data source that you use to check if the request is malicious somehow, compared to the data source that really operates on the codes, like invalidates the codes, they may not be in sync if they are different data sources, and even if they are the same data sources, but you allow for like parallelization of requests. So the first thing we could use, we are on a Redis meetup, so no surprise that we could try to use Redis somehow to do that. And by the way, these 2 red dots is something that we should probably acknowledge, and we should be able to live with them. And that's going to be really crucial in the next phases of the talk. So we could try to use Redis for that as a cache. So to offload the database, to offload the check of the codes used from our main operational database to the Redis, which is really good at looking up some stuff in some form of cache. But usually when we think of a cache, we think about the use case where Redis excels as well is like fetching the data for future use. Like you have something you fetch from the database, you have it locally, like in the memory, and you can really you can be really fast to fetch that from the cache instead of going directly to the database and paying the performance penalty and latency, all that stuff. So that's a pretty much like generic use case for cache, fetching data for further use, then storing them aside for the further use. But we can also like flip the question or flip the problem to check the cache not for the content of a cache, not for the content of the item itself, but just for a pure existence of an item in our store. So we can just check if the item exists or doesn't exist in a cache. And it looks like Redis sets are easy, like really first bet for that. They are good at it and they excel at it. So basically, Redis sets are just unordered collection of values. There are no duplicates like in a set theory. There's no duplicates in a set. They are blazingly fast. Most operations are O1 on average. It can be used to track unique values. So you can imagine a scenario where you use the code and you mark the code as used in your database, and there is a process. For example, the RDI on the new Redis that updates some set in Redis with a code that is already used, and it adds the code for the set, and then you can check the existence of the code. So first there's this sadd command, and then there's the sisMember just to check the existence, and then the sets have this nice property that you can remove the codes in case you have this use case to support that code could be reused, that you can manually remove the code and try to reuse it later. Redis uses hashes to internally stores the set, but it's just an implementation details. And the set has this property that whatever you put in the set itself, it grows kind of linearly. The amount of memory that it takes grows kind of linearly with the number of items put in the set, because it stores this exact item in the set. But sets looks like a cool and good approach to do that. So we can use the same picture, just like explicitly name the stuff that we will use. It's going to be Redis with this sisMember check. But then our business grows and changes. We can use we are using the Redis set. Business grows and changes. Service gets tractions, get more users. There are more issues, more codes that are issued to our customers. And there are fraud attempts growing together with the number of codes. And we also need to support the used codes indefinitely, because that's how it was designed. We don't want some code that was used like a year ago to be used again these days. So we need to like indefinite support for the code itself. And our business may come up with an idea of other one-off features to get introduced, like referrals, stuff that is, I don't know, like bonus codes, something like that, like things that are for one-time use, for one user only, when we want to protect the other usages of the same feature. So basically what we need is a need for speed, which we already have with sets, for example, but we need the space. We need some way of efficiently storing the content of our set in this case, for example. So data size is growing. The more items you put in the set, the more memory it takes. But we still don't want to trade off the latency. So we don't want to offload that stuff to yet another DB, maybe the separate instance. We don't want to trade off the latency, and we don't want to trade off the. We want to pay more for, again, yet another database. But we still want to filter out the malicious request. And this is kind of, there are kind of opposite forces in here. What if we could try to trade off confidence in the responses from our, let's say, shield from the very first stage for memory efficiency? And this is where probabilistic data structures come into play. And I believe this scenario is not the one that Max didn't mention in his talk, that probabilistic data structures, apart from counting, estimating the sizes and stuff like that, they are pretty useful, at least to me, from my like limited research, but it looks that they are really useful in domains like fraud detections, like estimating the stuff that, okay, this one may be fraudulent and this one is definitely not, for example. So they really excel at it. They are the structures that are not really known from the Redis, because as you all know, when we think Redis, we basically think cache. And again, if we think cache, we basically think Redis. But Redis has this probabilistics, difficult word, data structures. And what they are really space-efficient data structures that provide the approximate answers. So this is the trade-off that we are going to take and we are going to look at. So we are going approximate answers, but we are giving up the correctness and strictness of our answers, but we are getting more space efficiency, so we can put more data into our memory. They give us the fuzzy view on the data. That means that whatever you put for example, in the set, which is not a probabilistic data structure, you can put the data in and you can get the data out. The same data, the same item that you put in the set, you can get out from that set. For probabilistic data structures, whatever you put in the structure itself, you are not guaranteed. You cannot take the data. You cannot take the data exactly as it was that you put in the structure. They are designed to handle large-scale data with very efficient memory usage. We see that really matters when you have tons of the code, tons of this one-time features, one-time requests that you want to validate against. And they are used for big data analytics, caching mechanism like a supporting stuff, network security for the fraudulent requests or patterns, and fraud detections of various kinds, like in banks, like in online stores. It really depends on what kind of algorithms and what kind of fraud detection patterns you want to use. And basically, they contain like 4 structures. They are Bloom filters, cuckoo filters, count, min, sketch, and top K. These are the 4 that are supported. And we'll look at only these first 2 because they are suitable for the use case at hand that we have. And they are available in the Redis stack, which is now going to be probably, if I understand it correctly, Redis 8. And they are also available in Redis Enterprise, obviously. So the first one, the Bloom filter. How many of you heard about the Bloom filter before? Okay, just 2 people. Bloom filter, the first occurrence I believe I heard about Bloom filter was somewhere in academia back then on my studies. And then I saw it being used in, I believe, Cassandra internally, not as a data structure that is exposed to the end user, but like in internals of Cassandra database. But it's really simple conceptually and really nice in the properties data structure, which checks for a presence of an element in a set, in a group of the elements. What it can do, it can tell you, it's kind of weird, but it can tell you that the element is definitely not in the set. So if it's not in the set, you have like set of elements, and if the element is not, the Bloom filter is like sure that the element is not there. But if the element is there or may be there, it cannot tell you if it's definitely there or not. This is where the probabilistic, and this is where the probabilistic name part of the structures and the approximations comes from. Because if it's not in the structure, it's definitely not in the structure, but it may be in the structure. If it's not sure, it will tell you that, okay, the data may be in the structure, but I'm not sure. I cannot tell you that for sure. It's memory efficient because it stores hashes of the elements, not the elements themselves. So that's why I mentioned this before, that the input doesn't whatever you put in the structure, you cannot get out from the structure because it hashes the elements and it stores only the hashes somehow. And it trades off the accuracy for space efficiency, because if you have like bigger elements and you store only hash of it, the hash is kind of limited, pretty much, usually kind of short representation. You can put more hashes in the structure than the elements themselves. So it's trading off the accuracy for space efficiency. And you can start using Bloom filters like this one, bf.reserve name. The first parameter is error rate. So because the error rate in here, this is how sure the filter is what's the percentage of false positives. So what's the percentage of answers that it may give you the false positive, that element is not in set while it's actually not in the set. So the first argument is name of the structure. The other one is error rate, and the third one is size of the Bloom filter itself. And the funny thing is, I tried to do. Not sure if it's visible. I tried to do the Bloom filter, create a Bloom filter with 0.0 error rate, so that it doesn't give me errors, and it's not possible. It has to be in an exclusive range of 0 and 1. So we cannot do Bloom filter that is always right. Again, probabilistic data structures and approximation. So Bloom filter example, just to show you how it looks like. Let's work on a tiny filter with just 8 fields so that you can see that stuff. You add stuff to the Bloom filter, again, unsurprisingly with the bf.add. Again, any Redis commands are pretty self-explanatory and easy to remember. So you take bf.add, used codes, and some code. There's if you add an element, there are multiple hashing functions. Usually there's the same hashing functions that uses different seeds, which gives the different results in there. And the element is passed through that hashing functions, and it gives you an index. And an index, you get as many indices as many hashing functions you have. So we have, for example, this empty Bloom filter that has 8 slots. We have this index of the cell at the bottom, and on the top we have all the values set to 0. Empty Bloom filter, just freshly initialized. And then when we try to add the code, for example, ABC123, let's say that the hashing result for that ABC123 gives us the indices 2 and 6. So we flip the bits on the 2 and 6, we set them to 1. It's like third cell, because we are, again, counting from zeros, as normal people do. And then we try to put yet another element in our Bloom filter, D, E, F, 4, 5, 6, and the hashing results gives us the indices 3 and 6. So we put that stuff in there. The index 6 collides with the previous one for ABC123, but it's not a big deal. By the way, this one should be light green. It's not, like, as I can see. But still, now we have three bits flipped to 1. We don't. If there is a collision, like on the sixth index, we just leave it as it was. If it was 1, we just leave it as it was before. Only if it's 0, we just bump it to 1. So we never flip back from 1 to 0. And then, if we have that structure with 2 elements in place, we want to check if the next code is in our filter. And there is bf.exists. And then hashing results gives us indices 1 and 3. And we can tell now that the code definitely doesn't exist in a filter. Why? Because while the third index is 1, so pretty much it could be in the filter, because there is something that already hit that index, that bit on index 3. But we have this one index. We have this one index which is still 0. And remember from the slides before, we set both index or number of hashing functions indices are both to 1. So whenever at least one of them is 0, we are sure that the item is not in the filter itself. That's why that's why the Bloom filter can tell you that the element is not in the filter definitely, but if it is in the filter, it cannot really tell you that to be 100% sure. And then we check the code that we put previously in the filter, ABC123. It gives us the indices 2 and 6, and we see that we have both of them set to 1. That's why we cannot tell if this is the exact element that hit there, because as we remember from the previous slides, on the item 6, I believe, there was yet another element that flipped the bit that was included in that item. That's why if all of the hashing functions indices are set to 1, we cannot really tell if it's that element that is there in the index or if there are more that flipped the index. That's why in this case it cannot tell you really what's the it cannot be sure to tell you that the element is not or is not or is in the filter. Bloom filter parameters, because you can kind of tweak them on the creation time. You can define the max number of elements and the error rate that you want to do, that I was trying to cheat and set 0 error rate, which is not possible, apparently. It was already this 1 million size Bloom filter with error rate of 1%. There are additional expansion parameters. For example, if the filter gets filled, it kind of degrades a bit because the error rate starts to grow because you have all the cells flipped. So whatever you would ask the Bloom filter for, you will get a false positive. So then the Bloom filter does the thing that it creates a subfilter for itself with an expansion parameter, which is kind of controls the growth of the subsequent filter, and it goes through the very first filter, which gives always the false positive, like the positive answer, and then it checks the subsequent filter if needed. It degrades in the performance a bit, it degrades in the error rate a bit, but still it's pretty fast for that. If we can estimate the number of elements in the Bloom filter, we can avoid having this growth. There can be also a non-scaling parameter if you are sure that you are limited by the memory and you don't want to grow the memory. You can set the non-scaling, and then it's just the error rate that will grow with the filter being filled in. So with the Bloom filter, we can achieve the same. Again, these two red dots, we have to live with them, and this is where probabilistic data structures kind of excel. They will pass through some false positive that will probably filter out later in the stage 2 or 3, somewhere on our business logic. But what we get, we filter out massive amount of fraudulent requests, leaving the space and leaving the computation power and leaving the database capacity for our main processing, for our core processing in our services. But again, business changes and grows. We need to support code reuse. The fact that the thing that I mentioned before on the sets, from the set you can remove the code. So if you have, if we want to have the code that maybe was used incorrectly, or you just simply want to manually revoke the code and make it available again, that's something that we may want to implement. And Bloom filters doesn't allow deletions, because as you could see, we only store hashes and we like coerce them to bits and we flip the bits, and whatever, the only thing that we have in Bloom filters are just the bits, like bits that are set to 1. So we cannot really take the arbitrary element and remove it from the set, because we cannot tell. Again, this fuzziness of the data structure comes into play. So Bloom filters don't allow deletions. So should we go back to sets? Maybe they support deletions, but again, if we have a massive amount of data to support, sets may not be the right choice for us. And there is yet another data structure, this cuckoo filter. By the way, cuckoo, I was wondering what it is, and it turned out it's a bird, and then a bird in Polish, which is called kukułka, unsurprisingly. And the cuckoo filter is the name comes from the trait of the structure that I will reveal in a moment. It again checks for the presence of an element. It checks if element is definitely not in the set. So pretty much the same as a Bloom filter. So it works like from the outside, it looks pretty much the same. It's the only option in the probabilistic data structures in Redis that are available that allows for item deletion. So we can do that. So it somehow tracks the elements that are in the set. What it does, if there is a conflict, if you want to put element in the cuckoo filter, and it kind of conflicts in a way that we'll see in a moment, it kind of evicts the old element from its old position and looks for the next space for the element. That's why it's called the cuckoo filter, because apparently it's a cuckoo bird that does the same with its eggs. Like if it's if there is no space in the nest for the eggs, it just kicks out the existing ones from the nest just to place its own in there. Apparently the name is somehow connected. It's more space efficient on a bigger utilization, so the bigger elements you have in there, it's able to put them in a more concise way. So slightly bigger, better utilization of memory than in Bloom filters. The cuckoo filters are used instead of BF, they use the CF prefix, and they work slightly different. Let's imagine that we have this grid. Each vertical row, let's call it bucket. In this case, we have this bucket size of 2. That's why we have 2, let's say, levels of the structure. It works in a way that it again uses hashing functions, but the hashing functions give us the indices of the buckets. So not the indices of particular cell, but the indices of this vertical buckets. And what the cuckoo filter differs, where cuckoo filter differs from Bloom filters, it doesn't flip the bits. It stores the fingerprints or short representations of the elements. It's usually some shorter representation, like 1 byte or something of the element. And as I said, and on conflict, when both buckets are full, let's say for hashing results, our function gives us 2 possible indices. And if both of them are full, we are kicking out the existing item just to put our own, and we look for the yet another space for the old item. And let's see how it works in practice. Let's say we again want to add ABC123. For example, the fingerprint. Let's pretend that for the sake of simplicity, that's the first letter of the code. So fingerprint is A. Possible buckets are 0 and 7. It should be 1 and 7 probably. 0, 1, 2. Again, I messed up with the numbers. Anyway, these are the 2 indices that we got from the hashing functions. So we put the A somewhere in one of these two buckets. So we put it in there. Then we try to put the DEF 4, 5, 6. It gives us the fingerprint is D, and it gives us the possible buckets 1 and 5. So we put D, for example, here in one of the buckets in one of the cells. So in this case, we have a bucket size of 2, and these 2 buckets are fully free, so they have 2 slots. This one have 1 slot available, and this one have also 1 slot available. And then we are trying to put yet another code. We are kind of conflicting with this one, with D, which gives us 1 and 9 bucket indices. It conflicts with D somehow, but there's 1 more slot available, so we put G as a fingerprint in there. So we have this bucket which is full. Then we put some more codes in there. We put some more codes in there, and then we try to put we try to put MNO456 in the filter. It gives us buckets 1 and 7, and we can see buckets are full. Both buckets are full. So let's kick out the first the one item from the existing location. So this is what the cuckoo bird does, and look for alternative storage for this one. So it kicks out the G in this case and looks for the alternative bucket for G. So it puts the M in there and looks for alternative bucket for G. One of these 2 that was previously calculated for G. And it does that recursively until the place for the old element that was kicked out was found. And because of it keeps the fingerprints, not the bits flipped in there, it's allowed to track the elements somehow. It has generally lower false positive rates than in Bloom filters because it can somehow compare these elements, because it stores the fingerprint, so it can somehow compare, be more sure that the element has the same fingerprint or pretty much the same fingerprint as the one that we are looking for. So it's a bit better in this false positive rate. Allows for deletion. Again, we have this fingerprint and we have this bucket indices, so we are pretty sure that whatever we want to delete is already there in this particular index. There is a trick in the cuckoo filters. If it's not sized properly, if it's gonna be if it's not sized properly, there may be a case when it's full and it can no longer find new indices for the new elements. And when that happens, and then when max iterations parameters, max tries gets exhausted, it does rehashing, which is like performance costly operations because it does all that stuff, like rehashes all that entire structure. It takes some time. It's performance sensitive, so if you use cuckoo filters, you need to size that stuff. So it's really sensitive to the initial size of it. What's fun, you can add multiple copies of the same value, so it doesn't really work as a set. Because if you add the same value, it can choose a different slot in these different buckets. And the deletion of a non-existent element in the structure can damage the structure itself, because if you try to delete a non-existing element from the structure itself, it may think, again, probabilistic data structure, it may think that it's removing element that is actually not the element that you want to remove, and then you'll get skewed results after all, because then you'll try to look for an element which should be there, but apparently it's not there in the structure itself. It can create subfilters using expansions. Again, if it's getting full, it kind of expands, creates another filters that support the growth of the data size with the rehashing. But again, it conceptually works in the same way as a Bloom filter. It works differently under the hood. So with a Bloom filter, with a cuckoo filter, we can achieve the same results, pretty much filtering out most of the fraudulent requests with just CF.exist, and leaving again our main database for operational purposes. So what are the gains? If we look at the probabilistic data structures, what are the gains? Fast filtering out of fraudulent requests. Again, looking for the non-existence of an element in these two structures is blazingly fast. It's correct if it tells you that the element is not in the set, in the structure. It's for sure not in the structure itself. Core business logic, our core business stuff, so these two stages at the back are not impacted in any way. We just push the used codes somewhere from our infrastructure to the Redis itself, which we don't have to modify. We don't have to introduce fraud detection layers in our core business logic. We do all that stuff up front. We lowered our main operation database load, increased throughput through that database, leaving it available for all the other critical tasks in our infrastructure. And there's a really minimal additional cost. So if you have even if you're running Redis already and we are tight with the space, we can already fit in like really large Bloom filters or really large cuckoo filters because of the performance, because of the memory efficiency of these data structures. What are the downsides? Again, because of the probabilistic data structures, some bad requests can go through. But again, scaling distributed systems problems, we have to be prepared, and we have to have this last resort on our main database storage, which is always consistent. So that's not a big deal. Choosing the right structure and right parameters for that. Again, for example, for cuckoo filters, if we don't size the structure correctly, we may end up with costly rehashing, and for Bloom filters, we may end up with error rates raising at some point in time if we don't structure that structure. Don't size the structure properly. There are limitations with active replication model if you'd like to use it, because they are not replicated. From what I know, they are not geo-recreated in active model, so it cannot be used that way. But again, there are ways to deal with that. So it's all about trade-offs. Again, in like architecting solutions like that, there's no silver bullet. You can use sets, you can use cookie filters, you can use Bloom filters, you can use main database, you can use separate database for that. All of them have their own trade-offs. It really depends what you want to trade off for, what you are optimizing for. So Redis offers broad range of data structures for various use cases. So we see that there are sets that are kind of a different, kind of a default for that kind of operations, but there are these less known probabilistic data structures like cookie filters, Bloom filters. There are others for counting, as Max said, for counting, for rankings, and all the stuff that I didn't cover in here. So sets are good default. They are known. We know how they work. Probabilistic data structures are less known, but to me, it's really good to know about the fact that they exist and that they are available for regular use. They are not just on database internals in like deep in the algorithm somewhere in the code that you cannot use. And again, it depends on the use case that you have at hand. These structures really shine if you want to have like certain level of confidence. You can stack them. You can do several different checks against very small memory efficient data structures, and you can get more and more confidence about your about the frauds that are coming to your system. And if you cannot afford additional resources, if you cannot afford more memory, for example, if you have a lot of items in the structure that you cannot really fit into the memory, and you don't want to invest much into that, into the infrastructure stuff, and if you can tolerate some false positives. And then as we saw, we have to somehow tolerate false positives because we cannot really shield from all of them. So basically, choose the right tool for the job. Probabilistic data structures are one of these that is good to have somewhere in your toolbox, and use them if you feel that they are and if you validate that they are the right tool for the job. Thank you.